Hey guys, and welcome to a new video in this artificial intelligence tutorial. In this video we're going to have an introduction to reinforcement learning, and we're going to talk about the basic concepts in reinforcement learning and see what we can do with reinforcement learning. In later videos we're going to build on top of that, and we're going to talk about marker decision processes and some Bellman equations, and also some Q learning where we can have this Q learning where our reinforcement learning agent can learn from its environment by exploring and exploiting. So first of all, let's see what we can do with reinforcement learning. So first of all, I want to show you what reinforcement learning can be used for. And in this example here, we see OpenAI has implemented some reinforcement and learning agents that is operating this environment. Currently, now it's just playing Dota 2 against some of the world's best player and one of the world's best teams. And it actually beats the world's best team in Dota 2. And these are just reinforcement learning agents that are operating in this environment here. And then it just trained itself, it was playing against itself so many times that it just learned all of the different kind of things, and there's so many different aspects in Dota 2 that the reinforcement learning agents has learned by itself, and then it can actually compete with actual humans and beat one of the best teams in the world in Dota. So reinforcement learning can be used for a lot of different kind of things, and this is just to show you how far reinforcement learning has come already now in 2020. So first of all, we're going to talk about get an overview over the different types of learning we have inside of artificial intelligence, where in previous videos we had talked about supervised learning and unsupervised learning, where for supervised learning we're trying to make some regression on our data or some classification from images or data that we get. And if we have unsupervised learning, we don't really know what we get, and we try to make some associations with the data or clustering of the data that we get. Where we have the reinforcement learning here to the right, where we have an agent here that is operating in some kind of environment, as I just showed you with the Dota 2 example, where we have these agents that is just exploring the area or the game and the different types and combinations of the game, and then it is trying to reach some goals and get some rewards on the way. So for supervised learning, we have this labeled input here to a known output. So first of all, we have this labeled input here we give to our training model, or to our algorithm that is training our supervised learning algorithm. And then we get an output here from the labeled input, and then we can use supervised learning for classification and some other different kind of stuff. Where if we have unsupervised learning, we try to understand patterns and discover outputs from unlabeled data. So we don't know anything about our data. We just pass our unlabeled data to our explore pattern and trends algorithms, and then it tries to learn and learn and find the patterns in the data that was given, and then it tries to estimate some output or give some output from the unlabeled inputs that it has been given. Where when we're talking about reinforcement learning, it just follows more the trial and error method, where we have this agent that is operating in an environment to try to reach some goal, and then it gets some rewards on the way, and then sometimes it fails, it maybe gets stuck, or it loses some points or something like that, and then it just keeps using this trial and error method, so it just keeps getting better, and in the end it will find an optimal solution, and in this way here an optimal way through this library too. So if we're going to talk about the different types of learning here, if we're talking about feedback, where in supervised learning we have this label input that gets passed to our training model, and then we know the output, and then that output can be fed back to our label input again, because we are operating with known inputs and outputs. Where if we have unsupervised learning, we don't have any feedback, because we don't know if the output is right or wrong. So we can't feedback that to our input, because we have unlabeled input or anything like that. And when we're talking about reinforcement learning, we have this feedback system which is called reward system, and then the agents, it has an input state, and then the robot or the agent takes an action from that given state it is in, and then it takes an action in the environment, and then it gets a reward from the action taken in the environment, and it could be different kind of rewards, but it is the feedback from the environment to the robot, and then the robot tries to get the maximum reward all the time. So when we're talking about reinforcement learning, we need to talk about rewards and how we can define rewards and what different types of rewards the robot or agents need to get. So first of all, what is the reward, and how to find the reward. If you take the example here to the left with the car here that is driving around, it's a self-driving car, and we need to specify the rewards. There's a lot of different kind of rewards. Should we just specify that it gets a positive reward if the car doesn't crash, or if it doesn't like run over a pedestrian or something like that. And so we need to like define a lot more, and we need to take care of like a lot of aspects when we talk about rewards for like self-driving cars. We could like give our car a reward if it like took the right lane shift, or like took the right left or right turn. So we can like set up different kind of rewards, and then really like there will be different values for rewards, and then our agent or our car is trying to like operate around in the environment and trying to like maximize the reward. Where if we have this arcade game here over to right, like we can have like a positive or negative reward, and the positive reward is given to the agent if it gets a point, and if it dies, it gets like a negative reward, and then it just like tries to operate in that environment. So it's easier if you just have like some defined environment over here where we can just like specify a given reward, and then the agent learn from that. And it's a lot more complicated if we have like a self-driving car that's driving around in an environment with a lot of different kind of variables and different kind of things that needs to be taken care of. So there are a lot of different kind of like challenges in reinforcement learning, and when we have an agent, it typically has no prior knowledge, and it must learn how to solve a task through interacting with the environment. And then when it's interacting with the environment, the agent then receives a reward after, like it could be after each action it has taken, or like only from time to time. So if we have an example down here at the bottom here where we have an agent or a robot that is learning to play soccer, then we can set up the question like when and how should the agent be rewarded. And this is like, if we want to like learn a robot to like play soccer, it has no prior knowledge, then we need to like give it some different kind of rewards that it can learn from if it has done anything good. So we can say that we can give the robot a reward if it scores a goal, and then give it a negative reward if a goal is scored against it. But it will take really long time to like for the robot to learn to play soccer if you only gave the robot a reward from time to time. Where if we gave it a reward for like each action taken, or like more often, then it will like learn to play soccer faster. It could be like, for example, we give it a reward if it comes over the middle line, because if you're over the middle line, the probability to score a goal is bigger than if we're on our own half and stuff like that. So we can like, or like if it made a good pass or something like that, like we can give them different types of rewards, and then it will be easier to the robot to like try to maximize that reward and learn faster from the environment. So we need to like be really careful when we're specifying rewards, and like when and how we should like define our rewards, because our agent has no prior knowledge, and it must like learn how to solve the task all by itself, and just by interacting with the environment and then learning about the environment and exploiting the environment. So an example here we're going through in the slides here is the multi-armed or K-armed bandit problem, where we have the action A is like pulling a slot machine arm, and then each slot machine has a random payout function. So we don't know like the payout ratio or like the payout function for all of the slot machines. And then we want our robot to like try to pull the slot machines with the maximum return. So if we want to like have this bandit problem, we want to have our agent learning to maximize the reward and like get the biggest payout possible. So then we're going to talk about like the expected reward, because we need to like try to calculate the expected reward for the agent, so the agent can be able to like try to maximize the reward and get the maximum payout ratio. But we don't really know the expected reward beforehand, because as I said, like the payout functions are random for the slot machines and other reinforcement learning examples and applications. Like we don't know the expected reward, but we try to like estimate it at some specific time. So at some specific time step. So we have this estimated reward down here, which is big Q sub t here for some given action here. So we try to estimate the reward at the time step t for a given action. So we have this K-arm bandit problem here, and then on each state you choose an action from K possibilities and receive a reward for the action taken. So in this case here, we're pulling an arm, and then we receive a reward for the arm we have pulled, like depending on what type of reward we get, or lower like payout. And then the reward only depends on the action we take. And the expected value and the distribution are unknown, as we talked about on the previous slide. But nevertheless here, you must maximize your total reward. So we want our robot or like our agent to try to figure out how to maximize the total reward to get the maximum payout. So we must both like try actions to learn their values. We need to explore the environment. We need to like explore the different kind of slot machines, pull in different kind of slot machines. But we also like need to like prefer those that appear best. So we're exploring the environment. So we're just pulling the arms that we know that gives like the maximum rewards. So this is like how we can maximize the reward for the bandits. So like if we say like each bandit pay out a reward from different like probability distributions as we have down here, like we can have like some normal distributions or like random distributions and stuff like that. So the distributions are not known for the bandit, but the bandit like it tries to estimate the distributions and like try to find out the distributions, so it like knows how to maximize the rewards when it's operating in its environment. So one of the examples we could have like is the uniform bandit algorithm, and then we just pull each arm a fixed number of times, and then we return the arm with the best average reward. So we pull every arm in a slot machine. If we say we have 5 arm bandit problem, then we pull in all the five slot machines a fixed number of times, and then we can see like then we try to estimate the distribution for all the arms, and then we just return the arm with the best reward, and then we just pull that arm every time because it maximizes the reward that we get, or like the payout we get. But that's not really like the best approach to take like every time, because we could have like some payout ratio that only pays like out a couple of times, but then when it pays out we actually like hit a jackpot, and then we don't want to just like have to pull all the arm every time where we get like $2 if we like sometimes we get like $1 million in another arm. So we have this like trade-off here between like exploration and exploitation, and the difference is here like when we're exploration is like when we're exploring the environment, so we're like pulling in different arms on our slot machines, and when we are exploiting the environment, then we're using the information we already have about the slot machines, and then we're just trying to estimate or get the maximum reward every time we pull our arm. So suppose here you formed like the action value estimate. So we have this action value function here, and then we try to estimate it here with the estimated return. Then we can define a greedy action at time t. So we try here to define a greedy action that tries to like maximize the reward, because we always want our robot to try to like get the maximum reward and the maximum payout ratio when it's learning in the environment. But it is impossible to like both explore and exploit at the same time, so we need to choose like what we want to do that for like each times that we're going through. So we have this like action value methods, like the different kind of methods to like learn to estimate the action value values. But like one method and one of like more simple methods could be like just take the averages. So we have the sum of the rewards here for all the actions we take for a given time step. Then we just sum up all the rewards and divide it divided by the number of times that the action is taken for that given time step. So the sample average here, it tries to like estimate the estimates they converge to the true values if the action is taken like an infinite number of times. Like in practical examples, like we can't take an action like an infinity number of times, but the more action we have taken, like the closer we are to like giving it true values and estimating the probability distributions for like the multi-armed slot machines here. So this is like here where we have like this limit here going to the number of times action A has been taken by time t. It's going towards infinity. Then our expected return equals like the estimated expected return. So when we're talking about like this exploration and exploitation, we can talk about like the Epsilon greedy action selection method, where like in greedy actions we just select in like selection you always exploit. So we don't explore the environment. If we have the first arm here that just like pay out like 8 reward like every time we pull the arm, then we don't know anything about like all the other arms. We just like think this is the best arm, and we just exploit that and pull that arm like for each time step. So when we're talking about like the Epsilon greedy approach, you're usually greedy, but with the probability Epsilon, that you pick instead a random action for a given like a random time as well. So like we're pulling this arm that we think that is best, so we're exploring what we already know. But at some random time, which is like with the probability Epsilon, which we go out and explore the environment. So we try some other arms and see if they are better than the arm that we are like just exploring right now. So it's probably like the simplest way to like balance the exploration and exploitation trade-off, and it's often used this way here, where we just have some epsilon value that balances this exploration and exploitation, and it can be used for both stationary and non-stationary problems, which we're going to talk about as well. So we can talk about this learning right here when we're learning, when our model is learning, or like a reinforcement learning agent is learning. And the learning rate here, it represents like the speed at which a learning model learns. So like how fast our reinforcement learning agent learns. And the learning rate is really like a trade-off between the rate of convergence and overshoot. Let's say we have like a learning rate that is too low, then it will take a lot of time to get to like the local minimum here, like, or the maximum minimum here, like the global minimum here. And if we have like a good learning rate, then it will like converge really fast to like the global minimum. And if we have like too high learning rate, then we will never hit the the global minimum here, and we will only like hit the local minimums, and then we will never find like the optimal way, like the optimal expected returns and stuff like that. So if we have like too large or like too high learning rate, then our reinforcement learning agent will never get better on like each epoch or iteration. So like the times we run through our process. So we need to like define a good learning rate here, and it can both be static and non-static, the learning rate here, for each epoch or like for each step we take or iteration for our reinforcement learning agent. So we can see down here on the graph that if our learning rate is too high, we just like it just overshoots here for every epoch we take. And then if we have like a good learning rate, it just decreases over time. And if we have too high learning rate, then it just converges like too fast, and we won't get a better result like for more epochs. So we want like this steady decreasing function here for each epoch. So like every time we take more iterations or more steps, we just get closer to the global minimum. So we can also have these stationary and non-stationary problems when we're talking about reinforcement learning, where the non-stationary here is like the true action values that change slowly over time. And like for non-stationary problems, the sample averages is not a good approach, because we need to like use this exponential recency weighted average, because if we have a non-stationary problem, we can't estimate out in the future like what the expected return will be. Where if we have a stationary problem, we can just say that we just sum up all the expected returns, or like the expected returns for each time step, and we can just sum that up and take the sample average, as we talked about on some of the previous slides. But if we have this non-stationary problem, we need to use some recency weighted average. So like the next step we take, like it has like a more impact. Like the reward for the next step has more impact than the steps out in the future, or like the actions out in the future. So we can use this recency weighted average here, where we has like this A here, which is the step size or like learning rate that we talked about in the previous slide, and it can be constant for this non-stationary problem here. And then we just like try to estimate or find the expected value with this exponential recency weighted average method. So if we're going to like just take an example here to the end here, where we have a 10-armed, we have slot machines with like 10 slot machines here, and we're going to make a test here, and we can see that each slot machine here has like different reward or like different payout functions or distributions. So we can see down here that for each we have the actions here on the x-axis, and then we have the reward distributions up here on the y-axis, and then we run this test here for 1,000 steps and repeat the experiment 2,000 times with different bandit tasks, and then we try to estimate these reward functions here. So the more steps we take, like the more closer we get to the true values, as we also talked about, to like estimate the probability distributions, or like the expected value for each slot machine. So if we see the result here from the test, we can see that if we use this epsilon greedy method that we talk about, where we both exploiting the environment, and then at some given like random time we explore the environment and try the other arms as well. And then we can see if we don't use, if we're just greedy and we just take the best value here at the time, we don't get a really high average, and we're just around like 1 here. So the more steps we take, like our algorithm doesn't get better, or like our agent doesn't get better, because we're just greedy and we're not exploring the environment. We're just exploiting, and we're just using or like pulling the same arm all the time. And then we can change up the epsilon value here. So the more steps we take, like the more we explore our environment as well. So like like 10% of the times we're exploring the environment, and like 90% of the times we're just exploiting the environment, and we're pulling the best arm that we know of right now. So like it's not like necessary that the higher the epsilon value gets, the better our like average reward will get. At some point, like it will actually like get worse, and it will like return an average reward that is lower. But we need to like try to like different kind of epsilon values, and like just see what gets the best average reward return. And we can also see down here that if we have this optimal action percentage, then we can see that if we have this epsilon value here of 0.1, then we actually like convert this to like 80% optimal actions for like each step. So like every step we take, like we take like we take 80%. 80% of the times we take the optimal action, compared to if we just had this greedy algorithm down here, which didn't explore the environment and just exploited. Then we will only like take like 30 to 40% of the optimal actions for each step, and it won't get better the more steps which we take. So we want to like find this trade-off here between like the epsilon, like how much we should explore the environment, and how when we should exploit. So it's just like kind of like trial and error, and try to like tune these parameters here for the epsilon value. So if you're going to summarize and have a short recap of all we learned in this video here, we've talked about reinforcement learning and what it can be used for, and I showed you an example with the Dota example where an agent is operating in the environment, and then the agent is just learns by itself and playing against itself, and then it can actually like beat the world's best team, like the computer. It can just play by itself, learn everything by itself, and it can beat like the world's best team in Dota. So it's really nice, like what reinforcement learning has come to, and it can be used for a lot of different kind of things when where you have an agent that just like needs to get put into an environment and just learn how to solve a task, or like do some interaction with the environment. So we can also have this K-armed bandit problem here, where the true distributions of reward is unknown, but it is learned over time. So our agent is trying out the different kind of slot machines, and then it tries to like learn, or like try to estimate the true distributions of reward for all the different kind of slot machines by both exploring and exploiting the machines, and then try to like get the maximum reward for our agent. We also talked about this uniform bandit algorithm, and the exploitation. So this trade-off between these two, where we have this epsilon greedy method. And we also talked about the learning rate, which is also a parameter that we need to tune, and also like have this trial and error method that we try to like change our learning rate. So we try to like find the global minimum, but we don't want to like we want to like find it as fast as possible, but not that we just overshoot and we never get to our global minimum, and we only get to local minimums, which is not really good, and our agent won't get better over time if we only hit local minimums. And then we also have this stationary and non-stationary problems, where we talked about like how we should like look at the rewards in the future. So if we had this stationary here, we could just like take the sum of all the sums, like all the rewards in the future. Where we have this non-stationary problem, we need to like the next couple of actions, their rewards need to like be weighted more, so like they have a more huge impact. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you want more of it in the future. I'm currently also doing this computer vision tutorial with OpenCV, and an algorithm and data structure tutorial in C++. So if you're interested in one of those, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.